Alrighty folks, once again onto the breach, dear friends. We're back with our charger project. So what are we doing? This charger, as I've described previously, is broadly comprised of two power converter sections. We have a booster PFC stage and a buck charger stage. So common sense would dictate that on an initial test regime we would test each stage separately. Now in this particular design, as I've said previously, the booster power factor correction stage runs, it's basically a free running circuit, so as long as it has power it's basically boosting. So what I decided to do, when we last looked, I was yet to mount our driver board, so I have that done. Just use some very short pieces of flexible wire to the gate and Kelvin emitter terminals of our IGBTs. And what I've done is I've got a 12 volt power supply from a benchtop supply hooked in, and in order that we can simply pass the boosted power through the buck stage, I simply put a resistor, I believe it's a 470 ohm, let me see if I can get a little bit closer to that there for us. Some high quality camera work. And what we have is a little resistor from our 12 volts to our PWM input. And what that does is it simply powers the buck IGBT into a fully on state, and that basically lets us pass through whatever voltage that we generate from our booster stage straight to our output terminals without any buck converter action. So what I elected to do then is to very gingerly power up my PFC stage, and I actually did that a few days ago. I'd just like to share some of the findings. Now I've read the forum a little bit. I've seen some people struggling with the build on this particular charger. I've kind of anecdotally heard of a lot of people blowing up transistors and, you know, blowing up their builds basically. So just a few very simple tips for powering up, and indeed this is an old procedure I learned of during my time when I messed about fixing domestic appliances, TV sets, toasters, all of that kind of thing, in order to protect from potential catastrophic failure. Now this design obviously, you know, could have had any number of problems in it. It could have been, you know, bad connections, incorrect components, wrong connections. I might, you know, be totally off base with all of this potting compound. So basically anything can and will go wrong with a build such as this. So what we want to do always is to very gingerly bring the power up, and to always have a means to limit how much power that your unit can actually draw. I mean, when we actually think about what a buck converter does, this thing basically shorts out the mains. That's how that works. Or sorry, booster converter I should say. It shorts out the rectified mains, and that is a recipe for a bing bang boom if we have a you know, some form of a problem in our design. So what I did, came along, obviously this is a mains powered circuit, and the mains here is 230 volts AC. So standard 13 amp socket, plug, piece of cable. Now what you might be tempted to do is just, okay, well I'll just put a, you know, maybe I'll put a 3 amp fuse, or I'll put a 5 amp fuse into that plug or in line with my feed, and I'll, you know, just plug the thing in and throw a switch. Well, that will prevent, let's say, damage to your household wiring if there's a problem, but a fuse is not going to save your circuit from any kind of a major problem. What we actually need to have in series with our mains feed is some kind of a ballasting element. So my first power up test, I used a very common, well not so common anymore, but fairly common and fairly humble 100 watt filament light bulb. These have of course fallen out of favour in modern times in lieu of CFL fluorescence, and LED now seems to be taking over from the fluorescence. But a standard filament lamp has a very interesting characteristic for what we're wanting for a kind of a limiting ballasting element when we're testing a mains powered circuit, in that it's got a low resistance when it's cold, and it's got a much higher resistance when it warms up. So if we connect this in series with our circuit under test and throw a switch, well, it will allow current to flow, and if that current exceeds a certain point, the lamp starts to light up, and so its resistance increases and it limits the amount of power that the circuit can draw from the mains supply. And if we limit that power that the circuit can draw, then we limit any damage that can occur should there be some kind of an issue with our circuit. Now it performs another function, and it's something that you can very quickly get familiar with. It's how the lamp behaves when the circuit powers up. To give a few examples, if we throw our switch and the lamp just comes on full brightness as if it was just doing its normal job, well, that means that we have a dead short circuit somewhere in our circuit. If the lamp, for example, were to gradually illuminate and kind of, you know, glow in a kind of a dull manner, that kind of means that our circuit is drawing power, but it's not shorting out the mains, it's doing something perhaps that it should. And if the lamp blinks, that might mean that our circuit is shutting down, powering up, shutting down, powering up. And indeed that is exactly what occurred when I first connected my my charger via this 100 watt lamp to our mains feed. The lamp gradually increased and then started pulsing, and indeed I could hear a kind of a clicking sound coming from the inductors. So did a little bit of checking, and of course, sod's law, I had managed to have two connections swapped in the circuit. Basically the wire that senses the let's try and twist over a little bit, the wire that senses the mains DC bus voltage and the wire that senses the output voltage on our capacitor were swapped. I was tired when I was doing the solder connections, and the silk screen isn't exactly very clear, so I had managed to swap them. Now, had I not had a lamp in series when I hit that power, I would have probably popped something. I might have popped part of the control circuit, might have popped the IGBT, you know. So that was my first power-up test. So when I changed it around, got my connections right, powered up again via my 100-watt lamp, the lamp behaved differently, and it kind of lit up and went down and lit up and went down in a kind of a dimmer, as if I was just twisting a dimmer switch. I thought, okay, that's more promising, and we had a bus voltage coming off our output of around 240-250 volts DC, and there was no nasty clicking or thumping sounds coming from our inductors. So today I decided to be very brave and increase the amount of power that I was feeding to our circuit, because one of the things that would occur here is that this is a very large inductance. So the circuit has to charge that inductor the first time that it's turned on. It's got to build up a magnetic field in that and swing that field. So in order to do that, it's going to take a little bit of a shot of current to make that happen, and our 100-watt light bulb was basically limiting that current and preventing the inductor from fully magnetizing. So what I then decided to do was to put a ballast in there that would give me more current carrying capability. So I could have just paralleled up a bunch of light bulbs. I could have used a bigger light bulb, but I happen to have, you'll probably be, anyone that's followed the last charger build will be familiar with these electric cooker elements that I have. Indeed, I have about 10 of these. They're about 2 kilowatts each, and they let through, if you put them just across a mains feed, they let about 7-8 amps through them. So that's now connected in series with our 230 volts AC feed to our charger's AC input. So that lets, that would let a good few amps through. Could even be enough current to cause a problem. But from the initial tests with the light bulb, things were looking promising, so I decided to bite the bullet. Now what I've also got is my differential probe for the oscilloscope connected up to the gate terminals of the IGBT. You can see the two probes hooked in here. And what else have we got? Yeah, so over here then, as I was showing earlier, we have two 100-watt filament lamps connected in series across our DC output terminals, because when I first powered up I had one there and it's about 370 volts DC and it basically popped the lamp. So with two of them in series to share the voltage, they're perfectly happy. So additionally, over here I have a fluke, I probably saw it earlier, just have a fluke clamp meter reading my AC current input to the circuit. So that's enough of me talking. Probably everyone's clicked out by now anyway. So I'm going to go ahead. I'm going to take the camera back a little bit so you can probably see the flash and the bang if things go dreadfully wrong, which they usually do when I'm filming. Let me see if I can do a bit of a Cecil B. DeMille on this here. Finally found a use for my old SLR tripod. So I'm going to see if I can There we go, that's brightened things up a bit. Going to see if I can power this thing up. So I've got my trusty safety glasses just in case things do go pear-shaped. And so multimeter's just powered itself down. Let's go back on our AC current and go ahead, plug in and switch on. Now the first thing that I noticed was it took a 3 amp pulse when I threw the switch, and there's a kind of a clicky sound from my inductor. Now I've got on my multimeter 365.4 volts DC. As we can probably see, I've got my 2 filament lamps there glowing away merrily, and my scope is showing me a kind of a varying, fairly narrow duty cycle waveform on our gate drive. So I'll see if we can maneuver over to that. Should be able to see that now a little bit clearer, hopefully. It's running at 22.98 kilohertz. Sorry, it's about 23 kilohertz now. And I would imagine the duty cycle is low because we're only drawing a very small current from the circuit, so it's not really having to work too hard to boost up the voltage. I'll just try and lift the camera up there to the multimeter. Probably not going to come out too well, of course, because of all the crazy contrast I've got going on here, but might just be able to make some sense out of this, I don't know. There we go. There we are, 363.3 volts. So it's actually dropping slightly, which is a little bit disconcerting, so we're going to see what's going on there. Now, I'm also going to be looking to boost that voltage a little bit, because I know I'm going to need about 400 volts. So I'm going to have to look at the data sheet for that PFC controller chip and figure out what resistors and so on program the bus voltage, and see if we can bump that up to 400 volts. But that's about where we're at, folks. And let me check my mains input current at the minute. I'm at 0.7 amps RMS on my 230 volts. And yeah, my circuit's switching away merrily. So, I know, not very exciting, but nonetheless, fairly successful first power up test of our booster PFC. So I'm going to go ahead and mess about a bit more with this, and we'll see you guys all on the far side. Thanks for watching.